Hello, everyone. My name is Firas, and I'm a postdoc working with Dr. Melissa Green at Syracuse University. Today, I will be talking about thrust production and vortex shedding dynamics of oscillatory propulsors in inviscid flows. So this topic of propulsive performance of flapping or oscillating foils has been gaining significant attention in the past 10 years. Most of the current research focuses on flow structure, 2D and 3D, and their effects on time average performance. However, what we're interested in is the understanding of time resolved rather than time average fluid dynamic mechanisms that swimming fish tend to exploit. Specifically, we are motivated by the fact that it's currently unclear to what extent the wake structure can be used to infer the instantaneous thrust production. And we're also motivated by the fact that there is a clear lack of time-resolved data in the literature. So the objective of this talk is to explore this relationship between the instantaneous thrust production and wake dynamics of oscillatory swimming foils. Now I will briefly describe the methodology. I conducted inviscid numerical simulations using unsteady discrete vortex method. Here we are assuming an infinitely thin airfoil that is discretized into about 250 panels, and a point vortex is located on each panel. At every time step, a point vortex is shed into the wake from the trailing edge. The swimming motion here is modeled by the generic motion kinematics, pitching versus heaving, as described by these two equations here. The parameters that I'm varying are the Strohholm numbers and trailing edge amplitude. I'm specifically using these values here because they have been shown in the literature to result in efficient swimming performance. Note that for a given Strohholm number, the trailing edge amplitude and therefore velocity is the same for heaving and pitching. So really what we will be doing here is to compare the instantaneous thrust and wake structure of heaving and pitching foils. So before presenting the results, I'd like to describe how I am obtaining my force calculations. Rather than using the conventional Bernoulli method, I'm using the hydrodynamic impulse theory, as it allows us to explicitly highlight the mechanisms that flapping or oscillating foils use to produce thrust. Assuming a thin airfoil, 2D incompressible, fully attached flow, the impulse P is defined as the area integral of the position vector R cross the vorticity vector omega. Then the force is defined as the rate of change of the impulse with respect to time. Since we're interested in thrust here, we can take the axial component of the impulse, which is defined as the sum of the product of the circulation gamma and the cross-stream position y. Note that the circulation gamma includes the bound circulation gamma sub b and wake circulation gamma sub w. And then we can decompose the bound circulation into circulatory and non-circulatory component. The circulatory component is a result of the free stream and induced velocity by the external wake vortices, and the non-circulatory or added mass component is a result of the unsteady motion of the airfoil. Then finally, we can rewrite the axial impulse equation at the bottom left here. Once we take the time derivative of each of these terms, we then obtain the axial force and thrust coefficients of the total thrust, circulatory and non-circulatory thrust. Here I'm presenting the time-dependent wake structure of both heaving and pitching foils at a Strohholm number of 0.3. The top row displays the results of a trailing edge amplitude of 0.1, and the bottom row shows the results at the trailing edge amplitude of 0.25. Note that the panels are also colored by vorticity magnitude, which basically represents the distribution of bound circulation. It can be seen here that qualitatively, for a given trailing edge amplitude, the wake generated by the two motions look quite similar. Before jumping to transient thrust analysis, I'd like to briefly discuss the time average performance. I am showing here the time average thrust coefficient versus Strohholm number for heaving and pitching foils. It is shown that the thrust coefficient increases monotonically with increasing Strohholm number, and in addition, we can see that the effects of increasing trailing edge amplitude is actually quite different for the two motion times. For the heaving foil, increasing the amplitude results in increasing the time average thrust coefficient, whereas for the pitching foil, increasing the amplitude results in decreasing the time average thrust coefficient. To have a better idea of what's going on here, I'm showing the circulatory represented by the square symbols and the non-circulatory represented by the diamond symbol contributions to thrust production. We can see that for the heaving foil, circulatory mechanism dominates thrust production, whereas the non-circulatory has no influence at all. It is shown that as the amplitude increases, the circulatory contribution increases as well. On the other hand, for the pitching foil, non-circulatory mechanisms dominate thrust production, and it is shown that this contribution slightly increases with increasing amplitude. Whereas the circulatory component actually becomes more and more negative as amplitude increases, thus decreasing the total thrust coefficient as amplitude increases. Here I'm showing the instantaneous thrust coefficient for the heaving and pitching foils at a trailing edge amplitude of 0.1 for several Strohal number values, as well as the motion profile. We can see that for the heaving foil, maximum thrust is produced near the mid-stroke, whereas the pitching foil produces maximum thrust slightly after motion reversal. Furthermore, we can see that the Strohal number has a negligible effect on the timing of peak thrust production for the heaving foil, whereas decreasing the Strohal number for the pitching foil seems to delay the timing of peak thrust production. Here I'm showing the instantaneous thrust decomposition for heaving in the top row and pitching in the bottom row at the trailing edge amplitude of 0.1. It can be seen here that the non-circulatory thrust coefficient for the heaving foil remains 0 for the entire motion cycle. This makes sense because non-circulatory force is basically the force that is felt by the foil as it pushes against the adjacent fluid. Because the foil here is heaving up and down, the non-circulatory force is only felt in the vertical direction. Note that here I'm decomposing the circulatory thrust into contributions from bound, vortex, and wake or trailing edge vortices. Both contributions play a significant role in thrust production for the heaving foil. The sum of these two terms is actually equivalent to the suction force in thin airfoil theory. For the pitching foil, however, the bound and wake vortex contributions are shown to be almost equal and opposite, thus canceling each other out, leaving the non-circulatory thrust to be the dominant force. So we have seen that although the two motions produce very similar wake structure, the instantaneous thrust they produce is significantly different. In order to uncover the physics that may be hidden in the conventional Eulerian flow analysis, I am here using the finite time Litvinov exponent to identify Lagrangian coherent structures. So FTLE is basically a measure of the separation between particles in a flow. The FTLE field is obtained by integrating particle velocity to obtain particle trajectory. The particle velocity is directly calculated here using the velocity induced by each point vortex in the flow field. And since the number of point vortices can be quite large, the FTLE calculation can be computationally very expensive. To alleviate this issue, I am constructing a reduced order representation of the discrete vortices by basically combining them into larger vortices as shown in the images in the bottom right here. Now, the particle velocity integration can be either done in forward time to calculate positive FTLE ridges and can be done in backward time to calculate negative FTLE ridges. I am showing here on the top right an example of the positive and negative FTLE ridges, and as you can see, they provide a robust method of visualizing the wake. An important feature here that we'll talk about in the next few slides is the Lagrangian saddle point, which is located at the intersection of the positive and negative FTLE ridges. So here I am showing a comparison of the FTLE field and instantaneous thrust for heaving and pitching foils at a Strohal number of 0.3 and amplitude of 0.2. Note that the circulatory thrust is decomposed into contributions from the bound and trailing edge vortices. The objective here is to relate features that occur in the Lagrangian flow field that correspond to key events in instantaneous thrust production. Let's first look at this time frame where the maximum heaving thrust is produced. I mentioned previously that the intersection of the positive and negative FTLE ridges is known as the Lagrangian saddle. Here I'm defining two different saddle points, the formation saddle as shown by the green circle and the shedding saddle as shown by the yellow circle. The formation saddle indicates the initiation of the vortex formation, and the shedding saddle indicates the shedding of the vortex into the wake. There are two important things to look for here. First, the Lagrangian flow field generated by the pitching foil is shown to slightly lag behind that of the heaving. For example, we can see that the shedding saddle is formed by the heaving foil at this time frame, but has not yet formed for the pitching case. The other important observation is that for the heaving foil, peak thrust production correlates with the release of the shedding saddle from the trailing edge. In this time frame, we can see that the thrust produced by the heaving foil begins to rapidly decrease. This is accompanied by the acceleration of the shedding saddle downstream. On the other hand, the pitching foil is shown to produce minimum thrust when a shedding saddle is formed at the trailing edge. This is actually quite interesting, as the trend is the exact opposite of that of the heaving foil. As the thrust produced by the heaving foil continues to decrease, a new formation saddle is formed at the trailing edge, which indicates that a new vortex is grown. This seems to correspond to an increase in the trailing edge vortex contribution to thrust, as shown by the blue dashed line. For the pitching foil, as the shedding saddle is accelerated downstream, thrust begins to increase. It is anticipated here that the foil begins to push the adjacent fluid downstream, advecting the shedding saddle into the wake. At this time frame, we can see that the heaving foil produces minimum thrust. This seems to happen when the formation saddle is released from the trailing edge. For the pitching foil, we can see that as the thrust produced approaches a peak value, a new formation saddle is formed near the trailing edge. As the formation saddle accelerates downstream for the heaving foil, a pathway for the fluid is opened up near the trailing edge that allows the flow to be entrained by the trailing edge vortex. As the vortex grows due to flow entrainment, we see that there's a rapid increase in thrust production. On the other hand, for the pitching foil, it is shown that at this time frame, a maximum thrust is produced at approximately the same instance as when the formation saddle is released from the trailing edge. Thrust produced by the heaving foil continues to increase as the formation saddle keeps advecting downstream, as this allows the circulatory contribution to thrust to continue to increase. For the pitching foil, we see that thrust begins to decrease as the formation saddle experiences strong downstream acceleration. So to conclude, we have seen that in a time-resolved sense, pitching and heaving wake formations look quite similar. However, the thrust they produce is not. Through force decomposition, we saw that the heaving foil uses circulatory mechanisms to produce thrust, whereas pitching uses non-circulatory mechanisms, namely fluid acceleration due to the unsteady motion. We have done Lagrangian analysis using FTLE that shows the formation and the shedding saddle formed per half cycle that bound the formation of each trailing edge vortex. We saw that the circulatory force increases when the formation saddle is formed and continues to increase until a shedding saddle is released from the trailing edge. On the other hand, the non-circulatory force begins to increase when a shedding saddle is formed and begins to decrease when a formation saddle is formed. Finally, the bigger picture question that we continue to seek answers for is that, can we use this understanding of the different time-resolved force generation mechanisms to intentionally shape how we produce thrust in a time-resolved sense? This concludes my presentation, and I thank you very much for your attendance.